Well, it's a nice quiet morning here in Asheville, North Carolina. It's a Saturday morning. As we start this third chapter, which is titled Rainbows, we're going to be doing today geometry, a lot of geometry, and then we're going to do the derivative, calculus, max-min problem. So I'd like to talk a little bit about expectations in the course. You know, when you go to college, they say for every hour in class, you should spend 3 hours outside of class. That's what I was told. And many years ago, Chancellor Reed gave the same statement, and Reed Plaza, they named Reed Plaza after her. I think, though, here, this is a subjective matter. I mean, some courses take more time than others. It depends on your strengths and weaknesses, of course. Like it would be tough for me to take a poetry class since I tend to like math. And then other folks may have trouble with math. Since you're all in physics, taking this class, that means you're good in math. I mean, you chose mathematics and physics. But you know, it's a relative thing, and in your major, you really want to do well in your major, so you may want to do some extra. I remember when I was taking piano lessons at the university, you meet with the teacher for 1 hour, and they expect you to practice 20 hours before you come back. So that's like 20 hours for every 1 hour in class. So it's a subjective thing. Take advantage of my office hours where you can come to talk about things so I can save you time in doing homework. Take advantage of submitting homework early on a trial basis where I can look things over and give you some advice. Now, each teacher is different. Each teacher has different expectations, and that's a good thing. Because in real life, when you have jobs, you have different bosses, and one boss wants something, another boss, you want something different. And depends on where you are, you're going to have to, adapt. That's the way to do it. So my goals, what I see help you become a better scientist is to look at theoretical perspective. When I present material, being a theoretical physicist, I will show you derivations and the elegance of derivations. And when you do assignments, you want to do things on scrap paper first, so that when you turn in your assignment, it's neat. It's very neat. You recopy. You basically recopy. You never scratch out. That's what we're looking at here. It's like an engineering report. When you turn the report in, it's got to be neat. When I taught statics and dynamics for NC State, boy, they were so strict. And this is like, we're talking sophomores here. This is 200 level class where you had to have the diagram, had to have the given, you had everything, and then you had to lay out the discussion and follow all the steps. It would take maybe 3 or 4 pages, and you get like one number, and then they want you to box it off really neatly. Wow. So there's something to be said about that. That's preparing reports is very, very important. Now, when you're brainstorming or doing a session with other fellow, colleagues, other colleagues, of course, you're on the blackboard scribbling things out and doing all kinds of stuff. And when you take your exams, feel free to scratch out and do, because this is not a report. That's a polished report. That's not a homework assignment. When you're taking an exam, you want to get done as fast as possible. Time is of the essence. Neatness is not as important here at all, as long as I can read what you write down. So it has to be legible. But feel free on exams to cross out, and don't worry about being neat at all. Just get the job done. You don't recopy. You get the exam done, turn it in. So that's a different philosophy than, say, the report. When you turn in the homework, that's like a report. And different instructors will want different things. I tend to come from the slant of the engineering profession, where they do stress the neatness and the beauty and the elegance. And also being a theoretical physicist, I love the derivation. So it all comes together. So you have different teachers in college that look for different things, and that's very good. It's like real life when you have different employers that'll expect different things from you. So I hope that that's a good thing for you. And the time you spend on the course, you know, there was a political science professor, and I will not mention her name, that when I had this discussion with her, how many hours should you study for every hour in college? And you know what she said? And I was with a biologist. He and I were both there. She says, the answer is whatever it takes. And I looked at the biologist and says, whoa, that's hard. But we both agree that she was right. It's whatever it takes, that there are no guarantees in life. Sometimes you have to practice the piano an extra 4 hours you didn't expect to because you're having trouble with some passage is not quite working, or you're trying to make the team in basketball and put the time in. So hopefully you enjoy it. You love physics, you love mathematics. That's why you're in my class. And hopefully that's fun for you. And remember, I'm always here for you to help you when you get stuck in the Zoom office hours, or also through the email. All right, let's get on and do something beautiful, the rainbow. Introduction to rainbows. Before we do a calculation, let's look at a beautiful picture here of a double rainbow. We have the primary rainbow here, the brighter one, and the secondary one here. We're going to be calculating the rainbow angle today. So if you're standing here at UNCA, take your hand and stretch it, say, horizontal, that's 0 degrees. And if you were to then pick your arm up to point to the top of the rainbow, here the primary one, you'll find basically about, in fact, it looks like it's about halfway to the top of the sky. It looks like it's about 45 degrees, and we're going to find out more precisely what that is. And this one's around, this higher, it's like around 50 degrees. We're going to work on that. But this primary one does look like about halfway, up to the top of the sky, which should mean about 45 degrees. That was taken by photographer Mike Honeycutt. He worked at IT for many, many years at UNCA and had taken my class, and he works very hard. He was there at night one day in August 2003, and he thought of my class, and he took the pictures for me. So Mike Honeycutt, the photographer. Okay, so here I wanted to show you what is at the end of a rainbow. They say a pot of gold, but you see here it really is the a cup of coffee is basically what you find at the end of the rainbow. That's very, very nice picture there. Notice that the red's on top of that primary rainbow and the violet's on the bottom. And we'll be calculating those angles. Now, when you look at a schematic of a rainbow and the light entering, this is very, very exaggerated. The blue here bending a lot more than the red. I'm using blue for the violet end of the spectrum, the blue end of the spectrum, and the red end of the spectrum. And here, when the light hits the top of the rainbow, the raindrop, that's where you get your primary rainbow. We'll be looking at this more detail in a second. And then here, blue bends more, higher index of refraction for blue bends more toward the normal than the red does. Then there's a reflection where the angles are equal. And then they cross, notice that they cross so that the blue, when it's entering to leave, is on top of the red, but then it bends upward the opposite way when you go from water to air. And the highest drop in the sky, you're going to see the red. The blue will go over you. So you would see the blue from lower drops in the sky. So this helps us understand why the red's on top. And we said roughly it was 45 degrees by the other. We're going to show that today that it's going to be 40 for the violet, the lower part, and then 42 for the upper part, with red being on top. Here's a nice, beautiful picture of a rainbow here. This is from the courtesy of Todd Cravens from Good Free Photos. And here, you can really see the nice colors. You can see the reds on the top, then you have your orange, you have your yellow, green, blue, and violet. I like to think of 6 basic colors in the spectrum. I know Newton wanted 7 because 7 days of the week, seven's a magic number. But Crayola crayons goes with this 6: violet, blue, green, yellow, orange, and red as the big 6. So there you have it. Nice. That's the spectrum. So a lot of folks remember this as Roy G. Biv, where they have the red, and then you have, let's see, Roy G. Biv, here you go. You have the red, and you have the orange, yellow, green, blue, and then indigo, Newton put in there to have the 7. Violet. Although I did read a paper once that said that back in those days, the what they called indigo was more like what we call blue today, and what they called blue then was more like a cyan, because we do get a blue green in there. So that's interesting. That indigo may really mean blue, and blue may really mean cyan. Okay, so we have that, and then here for homework, you're going to be looking at the secondary rainbow. Here, light hits the bottom of the drop, and then there's 2 reflections, and when they cross again, the red and it goes over your head, and the blue, you get the blue from the uppermost drop, so violet. So that explains why in the secondary rainbow the colors are reversed. Now, before we do the calculation, we need to stare at a picture or several pictures to get a feeling for the angles and how things work. And these are difficult to sketch, so I drew them very carefully with a drawing program, and we're going to understand the relationship with the angles, and then we'll go to the blackboard, so to speak, and do the calculation. So here, there's a ray of light entering the drop, and it makes an angle alpha with respect to the normal. Normal is always perpendicular to where you're going to have the interface. And when you have a circle, any radius, any line from the center is going to slice the circumference as a normal. So these are your normals. Anything coming out of the center to the drop is your normal. It's very convenient. So when you bend toward the normal, according to Snell's law, you get then a sine of alpha is going to be sine of beta. You also get some reflection, which we don't care about. We lose some light there, reflection, we don't worry about that. And over here at the back of the drop, you get the reflection, so these angles have to be the same. And notice that this is a beta again, because since the radius is a constant, if you look at these two red lines, which are, radius, they're equal. So this is an isosceles triangle, and isosceles triangle has like the 2 angles are going to be equal. So you got the beta there, and then some light's going to sneak out the back. We don't care about that. The light go out the back here would, so this is normal there, would bend away from the normal, so it actually bend down a little bit. We don't care about that. So then you have another isosceles triangle here where these 2 sides are the same. So this has to be a beta down there. And if that's a beta, that means this has to be an alpha again, because if you run this backwards, entering the drop, that's alpha, that's coordinated with beta. Whenever you have an alpha entering the drop, you got the beta on the refraction. So here the refraction is the beta and the alpha is the incident if you're coming this way. So that's kind of very neat to have just 2 alphas and 4 betas. Very, very nice. So we're going to build up this diagram. It's going to get more and more stuff on it. So we're going to do this in steps. So this next step, what we have done is simply labeled the 3rd angle in each of these isosceles triangles. We have the 2 betas, and if you have the triangle, you're going to have 180 degrees, which is pi radians. So this is pi minus 2 beta to get you that angle there, and the same goes there because the isosceles triangle. Now down in here I introduced another angle, the rainbow angle, because this is the definition of the rainbow angle. If your hand is pointed horizontally, that's 0 degrees, and if you go up to where you see the light, that's going to be your rainbow angle. So now we go to the next diagram. What have we done here? We've added a little horizontal line here. And by adding that horizontal line, we can see that this horizontal line and this horizontal line are obviously going to be parallel to each other since they're both horizontal. And since this slanted line is in common to both of them, that you're going to have an alpha at the top equal to the alpha at the bottom. So they're both alphas. Now we're going to add a little more. We go to the next diagram. And here what we're doing is we're adding a horizontal line, and a slanted line is parallel to this slanted line. So I can reproduce this phi angle up in here. Now that means that this has to be phi because these are alternating interior angles, which I like to remember as the Z rule. I watched as a kid Zorro, and that's the fox in Spanish, and make the Z. So the alternating interior angles from your high school geometry, say they would be equal. And the diagram now has a richer amount of things on it. Now we're going to continue to the next one and watch what happens here with this next one. Wow, another alpha. Well, how did that happen? How do we get another alpha like in here? Well, let's think about this. If you look at this dotted slanted blue line, that's parallel to this, and that red line is parallel there. So and this is in common to both. So if you look at that, this is like a little reproduction up here of what you got down there. But probably the easiest way to say it is if this line is parallel, this blue one to this one, and this red dotted line slices both, then the two angles made here with that red line and the blue have to be alphas. So this is parallel, and that slices both. So that's very good. We're now ready to go. We're now ready to set it up, and then we'll go to the blackboard and do the calculation. We want to solve for the phi angle, and here's how you do it. This is cool. You take all the angles in here and add them all up, and you have to get 360 or 2 pi, because that would be the circle. So here I have, let's go ahead and start adding them up. So let's start with this alpha here. Put that alpha down there, and then let's go to clockwise. Then you got 2 of these pi minus 2 betas. So 2 times the pi minus 2 betas. And then if you come down here, the next angle is an alpha, plus an alpha, then plus a phi, and we're finished because we started with this alpha here. That's the alpha over there, and now we ended up with the phi. That has to be 2 pi, 360, because you went around a circle. And now if we look at this, we can combine some things. We have the alpha, first do some math, 2 pi minus 4 beta, and then plus alpha plus phi is 2 pi. And then here we can combine the alphas and get 2 alpha minus 4 beta plus phi. And guess what? 2 pi's cancel. They're gone. So you have this nice equation. And from that equation, we can write the phi on one side of the equation, and that would mean that you have minus 2 alpha plus 4 beta. And this is what we're going to work with. Let's look at a couple questions here. How do we get the numerical value for this angle? Like, aren't there lots of them? Because there's lots of places where the light hits the raindrop. Doesn't the angle depend on where the incoming light hits the drop? Doesn't the light hit the drop anyway and everywhere? So why is there a special rainbow in the first place? Now, when I was writing and preparing this, I got this permission from this artist. Amazing, beautiful, fantastic. This is Colin Leonhardt. This is in Australia. And it was the astronomy picture of the day in 2014. Just a beautiful, beautiful picture showing that a rainbow, see, if you're up high in the sky and you give the chance to see, you can see all of it. You can see a rainbow, a complete rainbow. And this is the secondary rainbow, see, where the colors are reversed. So very, very beautiful. So if you look straight on, head on, and then you were to go with an angle over to here, that's your rainbow angle. So you go over to there, and that's going to be roughly about 45 degrees. Notice that the rainbow angle for the violet, for the primary rainbow, will be smaller than the one for the red. Very close though, see? The angles will be very close. We're going to find those out next. But what about this, like, well, why do we have a rainbow angle in the first place? And this requires us to think about max-min problem in calculus. And here's the secret. This is the secret right here. The secret is that when the raindrop gets light from above, it's going to eventually go out. But notice that if it's higher, then the angle is steeper. See, this angle is not as steep as this one. Its slope here is steeper. But then if you go even higher, it goes back to being not as steep. Oh, that means there's a bundle of rays, right, where like a stationary point. So that means if I do the derivative and set it equal to 0 to find the maximum, that's the rainbow angle. That's why color and the light is going to be enhanced at that angle, because of this sequence of events. So when the light hits the top somewhere, you got an outgoing ray, and that outgoing ray gets steeper to a point, and then not as steep. So when light is hitting the drop everywhere, you're getting all these rays, but around the maximum is going to be a little enhancement, because to the left and to the right of that, you're going to have reinforcement. So that's the key. That's the key. And then once we have that key, we're ready to do calculus. We're ready to take the derivative and set it equal to 0, and then find what that alpha is, and then plug it back in here. But when we do that, we do have a problem, beta. We got to get beta as a function of alpha so that there's just alphas on the right-hand side. We can do our derivative. So let's look at this. This is the last piece of the puzzle before we go to the blackboard, so to speak, and do the calculation. Well, if we look at the alpha and the beta, we use Snell's law. N times the sine of the angle is n times the sine of the angle, and n is the index of refraction into 2 media. So this is air. So the index of refraction for air times the sine of alpha is equal to the index of refraction of water times the sine of beta. Now we know from the last chapter that the index of refraction for air is basically 1, unless you're doing a mirage problem where you have to have 1.00024 or 1.00026 or something really subtle. We can just take it to be 1. So we take the air index of refraction to be 1, and we set the water one to be n for now. So the connection is, when you have the sine of alpha is n sine of beta, we can then find beta as the arc sine of the sine of alpha divided by the n. So that's the key right there. So with that equation, we can replace then the phi function with just alphas everywhere. And we can now then take the derivative, because everything else is a constant. The 2, the 4, and the n, index of refraction, are constants here. So you take the derivative with respect to alpha and set it equal to 0. So we're going to now head to the writing of the equations and going back here to the paper, or I like to say the blackboard. And we'll show you all the steps, including a review of the derivative of how you handle an arc sine. And I consulted the math books to review, and I like to include that derivation because in the style of Richard Feynman and theoretical physics, you show everything. You don't rely on tables. You derive everything. So that's what we're going to do. So we'll head over to the blackboard. So we're going to calculate the rainbow angle, and we're not going to worry about dispersion, that is, difference between the violet and the red end. We're just going to take the index of refraction of water to be 1.33 and see what we get, and then later we'll worry about the dispersion. So here's where we left off. We have the phi angle is minus 2 alpha plus 4 beta. And we know that beta is given by the arc sine alpha over n. So these are the equations that we have arrived at from our previous analysis. And what we want to do is take the derivative with respect to alpha and set equal to 0 to find the rainbow angle. Remember that this phi is the angle that you have to raise your hand up to see the top of the rainbow. So this would be the top of the rainbow in the sky when you're looking at the rainbow. Now, to do this derivative, we're going to need to do the derivative of the arc sine. The derivative of the first term is easy, it's just going to be minus 2. But this one's tricky. Now, I don't know about you, but I would have forgotten derivatives of arc sine. I don't use them that often. But one of the goals in my course is to show you how to think as a theoretical physicist. And a theoretical physicist, Richard Feynman, my hero, would show everything for himself. He would just work things out. Now, of course, you're allowed to look up in calculus books to review, but the point is, what he would do is he would do the calculation rather than just go to a table. So let's look at this. Let's say y is the arc sine of x. Then we have the equation sine of y equals x. So I want to take derivative of this thing here. So let's start out by writing down y is the arc sine of x, and then from that you could say sine of y equals x. And now watch this trick. If I take the derivative of sine of y with respect to x, I get 1. Okay? But if we look at this another way, the derivative of the sine is the cosine, and then use the chain rule, dy dx. So you know you have the 1 because since this is equal to x, you know, dx is 1. But since you can always do the left side, by the chain rule, you would say that the derivative of the sine of y is cosine of y, and then dy dx. So once when we do that, we could see that dy dx is equal to 1 over the cosine of y. All right. But notice that, you know, this is what I want, by the way. This is the derivative I'm looking for. But notice that you do know that cosine squared of y plus the sine is the sine squared, that equals 1. And notice that since the sine of y is x, this term here is simply x squared. So that means that the cosine of y would be equal to the square root of 1 minus x squared. And since I want 1 over that, I then have my answer. In other words, d, since the y is the arc sine of x, then if I take that derivative, I want 1 over the cosine, so here it is. Now, I refreshed my memory. I checked some calculus books, but the idea is that you're not relying on the table. In other words, you're doing the derivation. So that's the derivation. So that's the hallmark of theoretical physics, to like check everything yourself. Don't look something up in the integral table, right? Could be a misprint. All right, so then what we are ready to do, this derivative. So now the derivative of the phi function, which you can explicitly say function of alpha, d alpha, that's going to be, the first term is going to be minus 2, and then plus 4 times the derivative with respect to alpha of the beta, which is this conglomeration of stuff. Like, look at all this. All right, so we have this over the sine. All right, so we're looking at the arc sine of, this is where you play the game. This is like the arc sine of u. So then this derivative would be, you have, say, a u there, and you're taking respect to alpha. Let's go ahead and write that out. If I have d alpha, the arc sine of u, I could do d du, the arc sine of u, and then the chain rule, du d alpha. And this is the same here, where you just put the u in for the x. So this here would be 1 over the square root of 1 minus u squared. And then here, du d alpha, well, what is that u? Well, that u is the sine of alpha over n. So if I do a derivative of this thing, I'm going to go cosine of alpha, and that n is a constant, so it just hangs around. So that means this derivative, this is the derivative here, the du d alpha. So if I put that here, I have the cosine of alpha over n. But I need to get rid of that u, and I can do that because here I know what u is. So I'm going to put that in there. Now it's going to be, a little messy. You're going to have a lot of stuff here. So let's go ahead and write this again. We would have here the d phi with respect to alpha. You'd have your minus 2, and here comes your 4. And now we have all of this stuff to put in there. So this is 1 over the square root of 1 minus, and the u squared is going to be then the sine of alpha over n squared. And then here the cosine of alpha over n. So that's the derivative. And that needs to be set equal to 0. But I don't like this complicated thing here. Let's bring the n inside the square root. If you do that, then you would have n squared, and these n squared would cancel. So you have a friendlier looking expression under that radical sign. And then cosine alpha over n is 0. So just bring that in inside here. It comes in as an n squared times the 1, and then n squared times the sine squared over the n squareds cancel, and you get this. So we're saying here is that 4 of these things, so 4 times the cosine, when I brought that n in, I don't have the n here anymore, so you want to take that away, because like we already brought it inside. So it's just the cosine of alpha, by itself. So this is 4 times the cosine of alpha, and that is going to be here over the square root of n squared minus sine squared alpha, and that is going to be equal to 2. So that's what we're looking at here, like this expression. It's looking friendlier. So what I would like to do is get rid of the denominator there. So we could write this as 4 times the cosine of alpha is 2 times the square root of n squared minus sine squared alpha. That looks good. And we can immediately divide by 2. So this is 2 times the cosine of alpha is equal to the square root. This is looking better now. All right. And we want to get rid of that square root sign. Let's go ahead and square both sides. So you have 4 cosine squared alpha is n squared minus sine squared alpha. And how about if we get the alphas on one side of the equation? I mean, we're really solving for alpha, right? So let's get alpha on one side of the equation. So we have 4 cosine squared alpha plus sine squared alpha is equal to n squared. Now, I like to write this as 3 cosine squared alpha plus 1 cosine squared alpha by itself, and you can see why I'm doing that. Because if you have a cosine squared and a sine squared, you're going to get 1. So that makes that sine go away. So things are even looking better. 3 times the cosine squared of alpha is equal to n squared minus 1. Then I'm going to divide by 3 because we're trying to get that alpha by itself on one side of the equation. So the cosine squared of alpha is n squared minus 1 over 3. And then the next step would be to take square root. So then the cosine of alpha is the square root of n squared minus 1 over 3. And then finally, you want the arc cosine, the inverse of the square root stuff here, n squared minus 1 over 3. So that's it. That's the rainbow angle. And that's going to be a little different from when you have violet and red, be a little range. But let's look at this a general idea of like what it is. So if we come up here and look at alpha as the arc sine, n squared minus 1 over 3, let's see what we get. Well, n is we'll use 1.33, and that is very close, to 4/3, and I love fractions, so let's leave it as the 4/3. I'm gonna eventually get you 2 significant figures. I'm gonna round off to I want this 42 degrees, 43, 44, that kind of thing. So I like to keep a little extra precision in terms of decimals in the calculation, round off last, so we don't round off our life away as we go along. So then n squared is going to be 16 over 9. Then n squared minus 1 is 16 over 9 minus 9 over 9. Oh, this is nice. Look at that. 7/9. Isn't that cool? And then n squared minus 1 over 3 is going to be 7 over 3 times 9. 27. Oh, that's cool. And then we need to do a square root. So alpha is going to be the arc cosine of the square root of 7 over 27. Very cute formula. I like that. And punching that out on a calculator, you get then 59.4 degrees. We'll keep 3 significant figures here, and then we'll round off later. And then what we're looking at is to do the beta, because remember what we're going for is that the rainbow angle is minus 2 of the alphas plus 4 of the betas. And the beta is equal to the arc sine of sine of alpha over n. So we have the alpha angle, but we need to have the beta angle, and then we're going to be finished. We figure it out. So what about this sine? Well, the sine of alpha would be equal to then the square root of 1 minus the cosine squared of alpha. So this would be 1 minus the cosine of alpha there. If you have the cosine squared, we gotta look at the cosine here. You can look at this thing here. You got the cosine of alpha is your square root of 7 over 27, because we took the arc cosine to get the alpha. So really this is your cosine of alpha there. And then if you square that, you get 7 over 27. So that's going to be then subtracted from 1 to get you closer. You get your sine of alpha, you take the square root. So this thing would be the square root of 27 over 27 minus 7 over 27. It helps me to keep my precision with fractions. If I were to start using a calculator, putting in all these decimals, things would get uglier. But this is a personal preference, and you might be different, and that's okay. We're all going to wind up with the same answer, but I like to keep these fractions here. Helps me keep track of what I'm doing, and if I make a mistake, I can go back and more easily find where the mistake is. So this is then the square root of 20 over 27. So for this beta is going to be, you first of all have to divide by n. So if we do that, the sine of alpha divided by the n is 4/3, so that would then flip to 3/4, and you have your square root of 20 over 27. And then for your beta, you want the arc sine of 3/4 square root of 20 over 27. So now use the calculator, and you get here 40.2 degrees. And now we're ready for the rainbow angle, which is minus 2 of the alpha, whatever the alpha angle is, plus 4 of the beta angle. So the alpha angle, that's your 59.4 degrees. And the beta is the 40.2 degrees. And then when you work this out with the calculator, you get here 42 degrees, which we had said earlier was about 45 degrees by looking at the photograph, looking at the picture. So that is very, very nice. Rainbow angle, 42 degrees. Now, to be more precise, where we want to figure out what it is for the violet and the blue end of the spectrum, if we look at, say, N for violet, now 400 nanometers, if you have here violet and then the red over here. See, this is your Roy G. Biv thing. So if you go this way, Roy G. So I'm going to leave the indigo out, since the crayons I got when I was in grade school, they had a violet, a blue, a green, yellow, orange, and red. They threw in black and brown, like the 8. So we'll use this term this way. And then I made up a mnemonic to help me with this. Very beautiful guys, you offer roses. Or it could be girls, guys or girls, doesn't matter. So here at this end of the spectrum, you have 400 nanometers. That's like the violet that's way on the left. And then if you go to the red way on the right, you got 700 nanometers. And there, you take these extremes to like get your extreme rainbow span from the violet to the red. So if you go with the 400 nanometers, the index of refraction is 1.345. And then if you go on the red end, that's going to be 1.331. We pretty much did the red one when we did the 4/3. We did the red one. So here what you're going to do is, if you go ahead and write this down again, this is the alpha is going to be the arc cosine of the n squared minus 1/3. So here for the alpha, that's going to be for the 400 nanometer case. Remember, your nanometers is 10 to the minus 9th. A nano means 10 to the minus 9th. Nano means a billionth. So you got the billionth, and sometimes you see the microns either, or the micrometer. This is 10 to the minus 6. So sometimes you encounter these. So like this would be like 0.4. You've seen this in a homework problem, 0.400, say, if it was micrometers, or they say microns. So if we do this with the index of refraction, you're going to get here the arc cosine with the 1.345, this squared, minus 1/3. And when you use a calculator, figure that out, you get 58.71 degrees. Now, I'd like to keep a little extra accuracy there to round off last. And then when you do the 700 nanometer case, you're looking at the 1.331 squared minus 1/3. And when you punch that out on a calculator, you get something close like we got before. We got 59.4, so this is 59.53. So then when you go for the beta angles, the beta angle, remember, is your sine, inverse sine of the sine of the alpha at the 400, and this is well, you just say n 400, so just we have symbols first. And that would be the inverse sine, the arc sine, and this is your 58.71 degrees, and then you divide them by your 1.345, and when you do that on a calculator, you get 39.45. And then for the 700 nanometer case, you want the sign of the alpha that goes with 700 nanometers, and then the index of refraction that goes with the 700. So this is going to be the sign, that's going to be the lower one here, the 59.53, and that's the 1.331 case here. And that is going to get you 40 degrees, and there you go, keep a little extra decimal point there after the decimal point. So then for the rainbow angle at the 400 at the violet end, you'd have -2 of the alpha 400 plus 4 of the beta 400. So that would be -2, and that would be your 58.71 degrees. And then you have a +4, and the beta, that's your 39.45. And now if I round off to the two, round off generously, when you plug that in and work that on a calculator, you get 40 degrees. And then we know this one's going to be, the second one is going to be what we got before, 42, because the 1.33 is very close to 1.331, but let's go ahead and just do it to be complete. -2, the alpha's at the 700, the red end, and the beta. So that's -2, and that's going to be your 59 degrees going in there, 59.53. And then we're going to have the 40.36. And that indeed comes out to be 42 degrees. So when you have your rainbow, the angle to the top, see red's on top, the angle to that top one, then you're going to have here the violet is on the bottom. So if you go up to the violet, you're going to get a 40 degrees, and then if you go up to the red, you're going to get 42 degrees. So you take your hand and go up to the sky like that, the rainbow, you're going to go elevation 40, rainbow angle for violet, the lower part of the raindrop, and the top one is going to be the 42. Now for homework, you're going to be working on the secondary rainbow where there's 2 reflections inside the drop, and you're going to find for the secondary rainbow, which is going to be higher in the sky, and the colors are going to be flipped, violet on top and red on the bottom, and those angles are going to they're going to be higher in the sky, so the red is going to get you 50 degrees, and the violet, which is higher, is going to get you 54 degrees, and you're going to work on that for our homework assignment. So here's a summary in the book of what we have worked out. The rainbow angles for the violet, 40 degrees, and red on top with 42. And for homework, you're going to be working on the secondary rainbow. Now I'm going to show you the diagram that you're going to be using for your homework. And this is it. So when you look at this, you can see that the light entered the bottom of the drop, and then you have the beta on the bottom, and you had a similar situation, the 2 betas, isosceles triangle, and then you have the reflection, you have the 2 betas, and you have another reflection, and the 2 betas. There's betas everywhere. So this is similar to the case we had before, but now we have 3 pi minus 2 betas. We have our line again, which gives us our alpha here, because this horizontal line, that horizontal line have the intersection with a slanted red line in common. The only thing that's different is what do we do with this thing? What is that? That's the only thing that's different, because these are very similar themes. that we have from before, the betas because of the reflections. So let's look at this. Well, if you look at how alpha and beta are coordinated, where you have alpha in air and beta in the drop, here is beta, and this has to be the alpha because they're coordinated. In other words, if you reverse the ray, send the ray the other way, then you would have an alpha ray going in, and you have to have the beta because air index of refraction times sine of alpha has to be in water times sine beta. So that means this big angle has to be your alpha. Now, this is the phi the rainbow angle is measured relative to the horizontal. So this is the outgoing ray, so that's the phi. And because of the z, alternating interior angles, this is also phi. But now we have the answer because, see, this cute little angle here, wedge angle, is the same as that wedge angle since you have two horizontal lines intersecting the slanted line. So this has to be up here, this has to be your alpha minus phi. And this has to be alpha minus phi. Now we're all set. So now you can now get the job done because alpha and beta are related the same way as before. The sine of alpha is n sine of beta, and then you do your trick. You simply add up all these angles and set them equal to 2 pi, and then you'll get a different formula than the one we had before. You'll get the secondary rainbow formula, but then you take the derivative with respect to alpha, set equals 0, and then you're home free. So that's what you'll be doing for homework. Let's look at some other rainbow effects before we leave this chapter. Alexander's dark band, the dark region. Well, we would expect this because, see, the color from the rainbow comes out at these very special angles. You get the maximization, you get the enhancement. So the other angles you would expect, like the angles in between, are not quite right. So there's going to be darker in there. And this observation was made about 2000 Common Era, so that's like 1800 years ago, by Alexander of Aphrodisias. So they called Alexander's dark band or dark bands. Dark band I like better, so like one band in there. And that's how it's known today. So Alexander's dark band. Now, also, there's this cool stuff. Before I go on, let's go ahead and credit the Petro Kretouchville, the photographer, who's very generously made these available for nonprofit educational use. And here, Mika-Pekka Markkanen, another photographer, with a gorgeous rainbow picture showing interesting, weird stuff down here. That's not rainbow stuff. This is complicated constructive and destructive interference. Like when you have waves, you have to go to the wave model now. The geometrical optics, the straight lines that we've been using so far in this class, is not enough to explain this. So when light comes from different path lengths, sometimes crest are with crest and they get reinforced, and sometimes crest meets the trough and get canceled. So this is interference effect that's going on there. That's called the supernumerary rainbow or supernumerary bows. Very, very nice. And then the tertiary. What about having a rainbow that is due to reflecting more times than 2? So here's a picture of the tertiary and quaternary, in other words, the triple reflections and the quadruple. And I believe this is the first time ever photographed, 2011. Michael Thusner, and published in Applied Optics. Wow, that's a research journal. These are very rare to see for 2 reasons. First of all, you get 3 reflections internally in the drop, and 4 reflections. That makes it very, very dim. Second, the reflections of these make it such that the rainbow is actually toward the sun. Now, you never want to look toward the sun. The sun is bright and it's dangerous to do that. But if you look in the general direction where the sky is near the sun, that's going to be brighter, so it's going to tend to make it harder to see these things. So that is wild. The tertiary and quaternary rainbow, the third and fourth case, and then technically a fifth and a sixth, and you can get all kinds of reflections, but dimmer and dimmer. So for the practical perspective, you're looking at the primary and secondary rainbow as being the prominent displays. And I wanted to go back and show you this gorgeous picture here of the complete primary rainbow. Beautiful, the circle. Full circle rainbow over Australia. Very nice. Okay, we'll see you next time.